For the past 7 months, me, Zolix, Moon, and Jazzy have been working on the end game music machine, the Maestro. We can play every note, every instrument at the speed of Minecraft. This beast is so insane, we're running into the sound cap of Minecraft. That's right, not the mob cap, but the actual limit of how many sounds that can be played at any given time, and it's all in vanilla Minecraft. Jazzy made a video about our journey to get where we are, and Zolix made a video detailing the technicalities of the machine. My role was in writing the code that converts MBS files into something the machine can process. This is fundamentally different from anything else you've seen before, and I want to focus on how we're storing and reading the music data. The project has been a roller coaster, and not the smooth kind. It initially started with this little falling edge 10Hz-ish note player that I designed, like a red coder that just needed a simple way to provide a stable, programmable 10Hz input line. I asked for help in Scribble server, and Zolix helped me out. They iterated on multiple variants until we ended up with something that could actually play notes at 20 Hz. So, we showcased it in one of Crafty's streams.
Ooh, that definitely sounds like 20 Hz. Which one's this? Megalovania? Let's see.
This is where the first iteration of code-generated structures came into play. It essentially sends 4 streams of redstone signals, where each signal strength represents a single slot out of the 15 here.
Sand Undertale, so true. Oh, what's this one? Turkish March.
Oh, no, this is.
They used... Why did they use chiseled bookshelves for this one?
When bookshelves are read by comparators, they give out a redstone signal based on the last book you interacted with. Minecraft actually just looks at the block's data and outputs the last interacted slot plus 1. This gives us an easy way to code a redstone signal with a single block. However, we ended up not using blocks like this because they take up too much space. Instead, we opted for another approach. We use Minecraft disks to store the data, and then read that data with jukeboxes and comparators. Every disk outputs a value between 1 and 15 when read by a comparator from a jukebox. However, the thing that's special with this machine is that each disk does not map to a specific note. Instead, a disk decides on which beat a specific note should be played. Let me try to visualize this, first using a simplified example, and then I'll show all the nuances of how we actually do it. Let's take this simple beat. Each dot represents if we play a beat or not. It's either play or don't play, like a yes, no, binary option. Wait, binary? Well, since it's just a sequence of plays or don'ts, we could represent those as ones and zeros. The magic happens when we decide to group these into chunks of 4, and suddenly we can read these as normal numbers in binary. In this example, we have the numbers 8, 8, 8, and 10. Since we group the binary digits by 4 bits at a time, we are guaranteed to only read a number between 0 and 15. With the exception of 0, which we'll get to in a minute, we can represent these numbers as music disks instead, meaning that the beat pattern we originally saw is now being represented by 4 music disks. This is the fundamental difference that sets this machine apart from any other. Of course, one drawback, you might call it, of this approach is that for every unique note that is played, even just once, needs its own separate data stream. I actually didn't like this idea at first, but the more I think about it, the more it makes perfect sense to do so. Some instruments create long streams of pauses just to play one note. But I think we've come up with a decent approach to represent this. I mentioned earlier that we can't represent 4 zeros for don't plays with a music disk. A disk always outputs at least 1. Instead, we use wool blocks. Specifically, we use colored wool blocks. There are 3 reasons for this. First, wool does not go into a jukebox, so no signal strength from it, which is what we want. Good. Second, we can stack wool blocks. See this as a compression technique. Since we assume pauses would be a dominant part of any song, this just reduces the amount of chests and shulker boxes we need. Third, by using colored wool, we can place back all the contents sequentially and have the exact same item order. If we didn't use different blocks or pauses, stacks of the same item would group up and create a different layout. If we check the contents of a shulker box in-game, we can see this pattern right here. Final note, we could have used any other stackable block, but we went with wool because YOLO. While I think it's quite verbose to include data for every note, the key feature of this approach is that we're able to play multiple notes and instruments at the same time, and thus, chords. This is a paradigm shift in how I've thought of note block players. Before, I've always thought of them as red coders, meaning one signal strength equals one note being played. The only way forward with red coders is to introduce more of them and somehow have the data split up and be sent to each of one of them. Eventually you'd end up with a similar situation to what we have here, where we have to provide multiple data streams to a bunch of different machines. If we roll back the idea of having a single stream represent all instruments at once, for a single tick, if we try to represent every instrument as either playing a beat or not, that becomes 400 plays or don'ts per tick. That's 2 to the power of 400 different states that needs to be represented. To represent the instrument playing with a single value, you'd end up with a number that's around 10 to the power of 120 large. In the observable universe, it's estimated that there are 10 to the power of 80-ish atoms. Relatively speaking, that number is nothing. It's kind of fun to think that every tick, our machine can be in more different states than there are atoms in the universe. Anyways, that is the fundamental principle. So far, I've been massaging you into thinking in terms of beat patterns, and if you understand this, you'll be able to follow along with the next part, how we're actually storing the data. Because of how the redstone machine is built, we actually do something similar to gray coding, meaning we don't convert numbers to binary, but we actually map disks to different specific beat patterns. There is a reason, and Zalex has a great explanation to why we're doing this in their video. This machine pulls items from chests and shulker boxes at hopper speed, which means do something every 8 game ticks. In order to reach 20 Hz, we need 8 bits of data every 8 game ticks. But each disk only maps to 4 beats. We're still missing half the slots. In order to reliably reach maximum speed and play at 20 Hz, or 1 beat every game tick, we do something really wonky. We take a note's full beat pattern and separate every other beat into another stream. Then do we apply the beat pattern to music disk method. This means every note has 2 streams, aka 2 chests with music disks. Then we read both streams at the same time, only we offset them by a single game tick apart, and then we interweave the signals while playing. This way we can achieve double hopper speed using only normal hopper disk readers. Now, where to put all those chests? The machine is big. So big in fact that we had to carefully fit all note blocks so they would be in hearable range. After 40 or so blocks, the sound drops off real fast. Looking from the top, this is where we stand to listen to a song. All the way back here is where all the chests will be placed. There is a reason why these are placed out so far, and I'll go over that later. It's a lot to take in how and where to place all of our disks, but let's break it down. We have 4 walls. Each wall has a bunch of note blocks with disk readers connected. The key point is that, although there are a bunch of different instruments in each direction, each wall follows the exact same layout. As long as we can place instruments on one wall, we can place instruments on all walls. Of course, there are some caveats, but yeah, this will get the main point across. The only thing that differs are the materials on the instruments in these 3 segments, which I'll call pseudo-instruments. They just represent some instrument, but we need to know which direction we're facing to know what instruments are on that wall. When we were building the machine, we just decided these 3 instruments go on this wall, and we put that into a little lookup table. The placements of our chest is a bit different than what we see on the wall here. We're actually placing chests inside the disk readers way behind the wall, which then have this very clean spaghetti wiring to connect them all. They're all still placed in a grid, which is something we'll rely on. We mapped out where each note and pseudo instrument goes on the wall, and using this, the code can calculate a local 2D coordinate. It's actually not that hard to convert local 2D coords to 3D. As long as we have a direction, we can just do a simple transformation like this. When we want to know what 3D coordinates of a certain note and instrument, we check the lookup table for which direction we should be facing, and then what pseudo instrument that instrument is. And boom, we have a 3D coordinate. Okay, caveat time. In order to fit all instruments, we put the percussions into the corners, but those instruments are cut in half and are connected to 2 different directions. In theory, this machine can transfer about 1 kilobytes of data every second. In practice though, we only transfer data when and where notes are playing. I mentioned this earlier, but there's a limit to how many sounds can be played at the same time, and we will actually run into lag issues before we are even up against the sound cap. Though it actually varies quite a bit how many notes per second you can play. Different instruments have longer or shorter play durations. And as an extra bonus, the lower the pitch, the longer the sound persists. I ran a test with all instruments at their highest and lowest pitches to see how long each sound existed in the world. This is the data I gathered from that, and they vary a lot. Now this might come off as weird, but I've measured this in seconds and not game ticks. It's because the length of a sound is independent of the game ticking system. This note takes about half a second to play. If I slow down time, this note still takes half a second to play, even if the rest of the game is in slow motion. Here's another weird thing about sounds in the sound cap. The Maestro uses hopper minecarts to pull out discs from jukeboxes, and for some reason every minecart always emits a sound up to 128 blocks away. That's why you needed to place these so far away from the center, otherwise all our disc readers would choke the sounds of the note blocks. Okay, final fun thing about the sound cap. If your sound cap is reached, the sounds in the main menu will stop working. There's an asterisk alongside the "can play any song" claim. How people usually create Minecraft songs is with Open Noteblock Studio, a free open source music creator that is specifically tailored to Minecraft sounds. When you save your song, you get an MBS file. This is what the code uses to generate all those disks and place them in the world. However, a feature of Noteblock Studio is to change the tempo. You can have the same notes play either slow or fast. The problem is that the Maestro is set at a fixed 20 game ticks per second. To compensate, the code adjusts when each note is played. If a song is written in 10 ticks per second, we just add an extra gap in between each note and it sounds exactly the same at double the speed. However, it becomes quite messy when we near speeds around 15 game ticks per second. We can't really add half a gap between each note, so we have to settle with something else. We essentially have 2 options. The first one is to adjust notes to match the tempo, but round their positions to the nearest beat. This will maintain the tempo, but will cause slight jitter in when sounds are being played. Just look at this weird spacing when we try to convert a song from 15 game ticks per second to 20 game ticks per second. The other option is to try to adjust the tempo to a fixed spacing pattern. The gang figured out a neat formula for our timing functions which specifies the spacing between any notes for any tempo. But it's not perfect. For songs around 15 ticks per second, the tempo gets shifted pretty heavily and some songs are barely recognizable. Just listen to Megalovania with this force-shifted tempo. I'll describe our formula like this. It's the best solution for the absolute worst case scenarios. For songs closer to 10 or 20 game ticks per second, it should sound pretty much the same. Oh yeah, also obligatory caveat, we can't play custom instruments or illegal notes, these red keys in MBS. We transpose every illegal note to be within Minecraft's range. I think that covers pretty much all that I wanted to mention about the Maestro. Go check out the others' videos too, they provide different perspectives on this whole machine. There's tons of other stuff that's not really that interesting, like what it's like to debug the machine or figure out what causes lag and yada yada yada. This project has been long in the making, and I can tell you 100% that I could have never made this myself. I barely did any redstone, this stuff's too advanced for me, but it did feel really cool to help out with all the code and be a part of this epic music machine. Bye!